were wrong.
Fool me.
Las Alamos is almost as good.
Yes. Yes, it is.
Now we are on the third day of the conference, and I think it's definitely clear that people are experiencing some fatigue at Zoom. I thought yesterday I would be less tired at the end of the day, but in fact it seemed even worse than the first day. So.
I'm sorry. I hope that at least some message.
Pues ya estamos en vivo en YouTube.
Okay. I think we can start if everyone agrees.
Jesús, no sé si vale la pena comentar, perdón, si que vamos a dejar entrar a los panelistas que han participado en diferentes sesiones, ¿sí?
Claro. Good morning, everybody. Welcome to the third day of the conference on applied category theory, graph operator logic, in memorial of Professor Zbigniew Osiewicz. Welcome again. Today we decided that everybody that was a speaker in this conference are sharing the conference like panelists. Then only one recommendation, please. Put off your microphone. You can start, put on and put off when you like, but please, during the presentations, be sure that your microphone is off. Then welcome again, and we are going to start with the first presentation. Go ahead, please.
So I would like to welcome this morning another distinguished speaker. Her name is Hannah Makaruk. Hannah is a scientist at Physics Division of Los Alamos National Laboratory in Los Alamos. She started work at LANL 25 years ago as a director-funded postdoctoral fellow. Her research includes mathematical, theoretical, and experimental physics. She is particularly interested in physics applications of group theory and quantum group theory, tomographic image analysis, gamma detectors, and nuclear data analysis. She received MSc in physics from Warsaw University in 1991, Warsaw, in Poland, and PhD in Applied Sciences from Institute of Fundamental Technological Research of the Polish Academy of Sciences in 1994 at Warsaw, Poland, for a thesis on group and quantum group models of the space-time, advised by Professor J.J. Slianowski. Hannah Makaruk is an author of multiple research papers, both open and classified, and over 30 invited and keynote talks at US and international conferences. Together with Robert Ozorek, for over 2 decades, she organizes yearly special sessions at the American Mathematical Society meetings devoted to inverse problems and to knot theory. For activities in professional societies, IEEE, AMS, American Physical Society, and promoting STEM education for young women. She was recognized as one of 12 New Mexico Women of the Year in 2018. And I apologize for having difficulty with pronouncing the names, but Hannah, please continue.
Thank you very much. Today, I would like to talk about SUN and other real algebra, as well as quantum group symmetries in physical systems, and how they play a fundamental role in finding analytical solutions for systems of differential equations, which describe those physics models. Of course, the first few words is about the memory of Zbyszek Koziewicz, and he was an influencing person in my life for over 3 decades of contacts at conferences and many out of conference discussions, scientific discussions, sometimes very emotional and but also very, very productive. He was not also a great scientist, but also a great person and great friend. And in the year 2000, when I had serious health difficulty and needed medical treatment, which was still not approved yet in United States, he, together with Micho Djurdjevic, organized my stay in Mexico and made this treatment available for me, for which I'm forever grateful. I also want to salute memory of Zbyszek by in the way that this talk will be in spirit of his research and his seeing what he thought about science. First of all, he encouraged not to be afraid of topics which are important, despite not being the mainstream approach to given topic at a moment. He was not a person who would be affected by trends and fashion in science, and was always telling not to be afraid of asking questions, asking fundamental questions, showing hypotheses which are open, which at this moment maybe we don't know the answer, but I hope that the questions which will be in the third part of my talk will stimulate the discussion, and maybe from this discussion some progress will be made. So I'm not showing only things that we know, but also present questions about things which I believe we honestly don't know yet. Of course, the memories of Zbyszek is not only work. We had also some excursions together. The most impressive for me was extra excursion in a small group of friends through Yucatan in 2006, and I was amazed by architectural and cultural richness of the ancient Maya culture, and I always stay impressed by the wonderful cultural things that I was able to see there. So let me start with introduction to talk. Then, when we are talking about solving nonlinear differential equations, denoted as ND in this talk, this absolutely standard approach is to apply the numerical methods only. And there is nothing wrong with applying numerical methods. This is a very powerful approach. The thing that I see as incorrect is thinking by many of my colleagues, especially in experimental physics and even more in engineering, that it is the only method which should be used for solving nonlinear differential equations. And my strong belief is that analytical solutions of those types of equations are still extremely useful. Not only useful, they are necessary for the numerical methods to exist, especially that the analytical solutions are essential for verification of computer codes, as we see that analytical methods enhance numerical stability, and also analysis of analytical form of solutions enhance our model understanding of the physics models. What I have to admit, yes, for nonlinear differential equations, analytical solutions are simply difficult to find. There are some classes of solutions about which we learn at college, which are, but for other types of solutions, it is not so easy to find them. Moreover, this type of equations usually don't have a single solution. There is always a family of solutions. So the task is not only to find a solution. The task is to find the proper solution that describes the physical system or engineering system or other system that from which we started. And applying the symmetry of this system, be it Lie group symmetry, or later I will discuss also the quantum group symmetries. This is the key not only to solve the problem, this is also the key to find this solution which is correctly describing the physical system we are starting from. So there are three main statements in this talk. In the first part, I present on some examples applying SUN and other Lie group symmetries of physical systems to solving differential equations. This is a powerful method. As any powerful method, it is danger. It has danger. And the second part is to illustrate that please never impose a non-existing symmetry on a physical system just in order to solve the equations. Because yes, in this method, this way we get the equation, the solution. Only this is not a solution that we wanted. This is not a solution describing the physical system that we started from. And it may lead, and it easily leads, I've seen multiple examples that it leads to simply incorrect answer to physical or engineering questions. The third part of the talk is about quantum group type generalization of Lie group symmetry solutions, and this is the part about questions and hypotheses. I would say that quantum group structures and those symmetries, they are in fact essential for for use and applications of Lie group symmetric solutions in the world of physics and engineering. Yes, we experience the Zoom fatigue, and if it is difficult to pay attention, and you would remember one sentence from this talk, please remember that Lie and quantum group symmetries are very powerful. They allow us for finding new analytical solutions from nonlinear differential equations. A lot of pictures here is from meetings of American Mathematical Society. And yes, we are running this inverse problems series of meetings for over 2 decades. Then Zbyszek frequently participated and was a fan of those meetings. And the next meeting, also in memoriam of Zbigniew Osiewicz, will be held 23rd and 24th of October this year. Many of you already agreed to be speakers at this conference, which we are preparing. And thanks to the fact that American Mathematical Society is making this year meeting totally virtual, it is available to everyone. So if anybody is interested in seeing this meeting, please let me know, and I will gladly propagate the link to the American Mathematical Society. Of course, you will need to register to the whole conference, but the registration fee is rather limited. Let me start from the first example of power of this symmetry method. This is an analytical solution of Dirac equation in description of conducting polymers. The polymer that we discuss here is polyaniline. Please, there is an image of monomers of polyaniline on this screen. The macromolecule is extremely long. It is tens or hundreds of thousands of such individual monomers. So this is extremely long, practically one-dimensional molecule. And the polymer material built from polyaniline wouldn't be much different from any other polymer, except when it is prepared in special way, in such way that all those micromolecules are strengthened into straight lines parallel to each other. Then polyaniline conducts electricity. Actually, it is as good conductor as metal, but only in one direction, in direction of those micromolecules, and it is not conducting. The sample is not conducting in any other direction. So this property depends on internal symmetry of the material, and we already see that SU2 symmetry has some information about conductivity. It is important property. The other thing is that experimentalists know that the electric charge carriers in this material are so-called polarons, which are constantly created and annihilated inside those huge macromolecules of polyaniline. this is creation and annihilation. Aha, we are in the room of truly relativistic quantum physics. And so the note that this is something which should be described by Dirac equation. Most, and up to my knowledge, practically all of the software for chemical computation is based on Schrödinger equation. And it works very well in most cases, but of course not in the relativistic case. The moment when I entered this research was a question that experimentalists measured polaron energy spectrum, and it was clear, well visible spectrum. Yet on computer simulations, one of the levels was visibly missing, and it was missing despite that it was seen in experiment. The thesis, of course, is, aha, this is how polyannealing lets us know that that we are in room of relativistic physics, and we need to solve the equation for the Dirac equation. SU2 is important, so we need to solve Dirac equation on a curve manifold SU2, so we are in the room of nonlinear differential equations. To effectively solve it, the information that is needed is that fortunately SU2 and three-dimensional sphere manifolds are equivalent and as manifolds. So thanks to this, spinor structures over them is isomorphic. And here is in telegraphic shortening just the spinor structure which allowed to found the spectrum in this notation. And if anybody is interested in this or other examples, please let me know, and I would gladly expand in the talk in October, because I intend to the October talk to be like zooming in on one of the topics from this longer talk. So in this diagram, horizontal arrows mean action of group on spaces. Vertical arrows are covering maps. And the Dirac operator acts on vector bundle associated with the principal bundle represented by the spinor structure in this diagram. So this proves that we would have the same spectrum as of Dirac operator as on three-dimensional sphere, and this spectrum is known, and it is equally spaced spectrum because it is n when n is integer plus minus n plus 3 over 2 times experimental scaling factor in units of energy. And so in this way, the experimental puzzle was solved. We know that polyannealing is a truly relativistic quantum material. We are going to next example. This is about Euler equation for incompressible non-viscous fluid. It is widely used in numerical modeling of many phenomena, including weather predictions. The standard method for solving for numerical approach is Belking method, very efficient numerically. Unfortunately, this method is numerically unstable. What limits the evolution time of the modeled system, and it limits how well those models can predict, for example, weather into the future. And modeling of weather using Euler equation is very, very good, I mean, very well predicted. Fortunately, we can use symmetry of SUN algebra by applying observation that structure constants of this algebra produce structure constants of area preserving diffeomorphism over two-dimensional torus when n is odd and is huge, going to infinity. Numerical method based on SUN structure was tested against Galerkin method on the same hardware, in the same programming languages and so on. And it is at least order of magnitude, sometimes 2 orders of magnitude, more stable in the time of evolution of the system. So analytical solutions and group symmetries directly support the numerical methods. Wow. So symmetries are so powerful. Let's use them everywhere. This is another picture from our meetings. Well, yes, it is good to use them. No, as any powerful method, abusing of this method is extremely dangerous. So please don't produce a model of spherical curve. Use only the symmetries which are the real symmetry of the physical system, not just a symmetry to solve the equations. And I've seen really good scientists falling into this trap. And the main reason, I believe, is that implicit assumptions about symmetry are not examined, and that our human, even scientists' human intuition is mostly for linear problems. And when we are dealing with nonlinear differential equations, it is not so easy to spot if the obtained solution does make sense or it doesn't. The first example, it is from discrete mathematics. So this is difference, not differential calculus, but the idea is the same. It is about hardware, neural nets for artificial intelligence. And this is, now it is widely used, the multi-layer spacey connected neural network, as it is on the image in the right. Yet when we were discussing and doing this problem in the 90s, the prevailing design was 2-layer neural network with densely connected nodes. This design is, as electrical engineers taught me, extremely difficult to implement in the hardware, while the sparsely connected nodes are easier to implement. A neural net expert, Valeriu Beiu, with whom we worked at Los Alamos National Laboratory at this time, had a strong intuition that the multi-layer deep neural net architecture should be optimal. Yet all calculations done in literature then, and he repeated it, shown the 2-layer neural net being in advantage. Those calculations were optimizing information flow by optimizing the extrema of entropy. And when we examined this with Valeriu Beiu, problem was not in the assumptions, but in the method of calculations. I mean, steps was assessing n-dimensional volumes in really high dimensional spaces. And as much as it was Euclidean n-dimensional geometry, still it needs some computational effort and skills to exactly compute such volumes. So the method used was, okay, we are comparing which volume is bigger, so let us circumscribe by n-dimensional ball each of the volume and compare volumes of those balls, volumes of n-dimensional balls in Euclidean geometry are known in any dimension. So it was easy to calculate. Easy, unfortunately, doesn't mean correct. And applying this not existing symmetry caused the wrong result, and it is we can illustrate it in three-dimensional geometry. The problem is that when we are comparing a cube or other volume in which sizes in all dimensions are very similar, it can be circumscribed by a ball which is much smaller than a smaller volume which has size in one of the dimensions much bigger than its sizes in the other dimension. So after the correct volumes were computed, this allowed to prove advantage of multi-layers neural network. I hope that it was important for the science. At least our paper is very heavily cited. The next method, which is extremely widely used in experimental science, it is so-called inverse Abel transform. The method is that a radiogram of axially symmetric experiment or axially symmetric object is done, and then from this radiogram, the inverse Abel transform allows to recreate the three-dimensional volumes and their densities, under assumption that this axial symmetry exists. And this method is extremely widely used in experimental physics. And it works. It works despite, as we know that in physical world there is no ideal symmetry, but as long as the axial symmetry is more or less correct, it works. However, once my colleague came to laboratory, and I'm not saying the name, but I greatly respect this scientist, and he thought, wow, in my last experiment, I've got microscopic volumes, like cubic centimeters of negative density. Think it was like -5 or -7 grams per cubic centimeter. Have we obtained completely new physics in our laboratory? Well, we didn't think so, of course. And the problem was that apparently it was experiment involving explosives, and a blob of matter was dynamically flying out, so the symmetry was broken. And when we realized what was going on and not applying axial symmetry, then the calculations were exactly correct, and with the simulations, and we were able to recreate both the place and density of steel balls used in our experiment. Nevertheless, when there is no such big blow of the symmetry, the inverse method inverse Abel method works and is applied every day in hundreds of experiments all over the world. Now I'm coming to the most difficult part, the part of questions. And I need like Spirit of Zbyszek tapping me on the arm and saying, yes, Hannah, you should ask the questions. You should state boldly what we don't understand yet in science and steer the discussion, because from this discussion, hopefully the real progress in science will be born, not if we state only what we already know, there is in a sense no progress. Let me say it. Mathematics is exact. We obtain Lie group symmetric solutions for nonlinear differential equations, and they are singular. There is no neighborhood of approximate solutions around them. It was stated in a number of papers by different scientists from approaching different solutions, that those solutions are so perfect that they cannot be realized in physics. Yet we know that they are realized in physics, and inverse Abel method applies in laboratories. Conducting polyaniline and thousands of other examples tell us that Lie group symmetric solutions work. So how is it possible if in physics and in engineering any symmetry can be only approximated? We never produce geometrically perfect ball, geometrically perfect axial symmetry, or for that matter, anything microscopic which is geometrically perfect. And my hypothesis is that those neighborhoods exist, that they exist mathematical structures, probably quantum groups, or maybe those are not defined yet, weaker structures, weaker than the quantum groups, but in essential something that provides the neighborhoods to our solutions, otherwise the solutions would not exist. And the one, I'm now just in telegraphic mode. One of the examples was error-protected states for quantum computing. We know that quantum state errors are the fundamental problem in any quantum computations. Zanardi and Rasetti found quantum state error avoiding property based on dynamically algebra symmetry of those states. However, in their own papers, they stated nobody would be able to achieve it because this is a singularly algebraic solution. We examined this solution and discovered that the assumption of Lie group symmetry could be made, which they used for the construction, could be made weaker, and the construction is preserved for any object with a Haar measure. And we proposed a quantum group with one-dimensional parameter of deformation to produce the neighborhood and to produce more physically obtainable solution. Of course, Zbyszek was very active in gravity. I'm not even talking about this gravity example, except of saying that when general relativity is put in its general form in Weissenberg and invariance, we can find Weizenbeck invariant, we can find four-dimensionally algebraic solutions. Three of those algebras are equivalent to a flat cosmological solution because they have vanishing Riemannian tensors. But the fourth solution, truly four-dimensional algebra A46 is equivalent to a non-flat cosmological solution known as Petrov solution with certain value of parameter. So this is a huge topic. I only stating that this shows that also general relativity has solutions with quantum group type symmetries. And in my understanding, this is how the symmetric solutions like Schwarz solution could exist in astrophysics. The last example, but very, very important. Trzęsowski and Sławianowski provided classification of all possible three-dimensional dislocation in continuous media using Bianchi classification of 3D Lie algebras. It is important for engineering because engineers are always concerned about materials losing its mechanical properties by aging and by developing those dislocations. However, just to classify the problem doesn't make us closer to solving it. So after starting from this classification, we shown that there exist quantum group solutions for the quantum groups for the quantum group generalizations of some of those algebras for those which were already defined in the time we are working on that. And this construction describes not only existence, but the very process of forming and creating those dislocations. So what is important, what is always important in engineering, but it is also important for the question that I want to ask, because if it is true that quantum groups or similar structures possessing Haar measures are in fact neighborhoods of Lie algebraic symmetric solutions, then we get, at least for three-dimensional Lie algebras, something like physics experimental methods for verifying for which Lie algebra quantum group types are. This type generalizations can exist and which cannot. And the experiment that I'm suggesting that maybe it would be worth to make is simply to examine all the possible defects which we found in three-dimensional samples of continuous media like concrete, like piece of old rubber and so on. And if my thought process is correct, only those Lie algebras which possess the neighborhood should be realized in the physical world. And if any of those algebras cannot possess a neighborhood defined in such sense, we would not find defects in continuous three-dimensional media which are described by this symmetry. I know that this is a very, very broad statement, but this is just what I started to be convinced when preparing this talk, that quantum group should provide the neighborhood for a Lie group symmetric solution of differential equation. Either or this solution cannot be realized in the physical world. I also believe that all this research is only a beginning, and there is so much we can do using the powerful method of Lie group and quantum group symmetries. I also encourage, I welcome the discussion. If we will not have time, I will discuss with everybody offline, and also please suggest if you want to hear expansion of one of the examples or a couple of examples in my next talk in October. Please tell me what you are the most interested in. Thank you. Questions?
Thank you, Hannah.
Do you hear me? I don't hear.
Yes, thank you very much, Hannah. You are finished ahead of time. We do have time for questions. Anyone who is okay, I think I see one person with a hand up. Yorsi Koshek is. Oh, there he is. Okay.
Okay. So I have a question. This is a really beautiful stuff, very rich. It would be great to see actually some examples of when the method doesn't work, particular method of symmetries doesn't work. But so the question would be, are there any mathematical tools which allow you to detect that your method doesn't work, or only, you know, just the ultimate answer doesn't match reality? So
Okay.
these tools would be interesting to have, right? But then would be a question whether the tools also have some bias which would have to detect with other tools. Okay, so maybe I'll leave it with that.
So this what you asked is in a sense a fundamental question. I didn't go in this direction because it is rather complex. So there is no algorithm, no general answer like do this and that, and you find the symmetric solution. This is why I call it method, not an algorithm. Every time it worked, it came from real in-depth understanding of the physics of the system and what is the symmetry that is crucial for the properties of the system. Sometimes it is obvious, it is a symmetry which we put into axially symmetric experiment because we want to do the radiogram and want to use inverse Abel transform. So the experiment itself is designed from the very beginning to possess a symmetry that allows to solve the equations. Other type, it is like the example with polyaniline, where the physics also, I believe that physics tells us what type of symmetry is important. In polyaniline, it doesn't conduct electricity, or it conducts very, very weakly. When molecules are not straightened, and when they are straightened into straight line and parallel to each other, the properties of the material change, and material conducts electricity. So this is why it was my assumption that this symmetry is essential for the property. This is why when we build a model, this means that this model is also always an abbreviation, like we are considering only limited properties of the system, but this property of the SU2 symmetry is important for the conductivity, so it has to be represented in our model.
We have 3 other questions.
Yes. Let me just only. I will answer all the questions not now online, but offline. But this is important. In most real life cases, when we have a physical system, it is difficult to find the equations which properly describe it. Not only to find the proper symmetry property which allows to find the proper solution. This is why, as I signalized, frequently people found and proceed in good faith with non-existing symmetry. Yes, there is like no one strictly mathematical method. We always have to start from really in-depth understanding of the physical process that we want to model, and answer first in physics what is the symmetry important for this physical system, crucial for this system, then build a model around this symmetry, then solve the equation. Thank you. The next question.
The next question, Garrett Sobek.
Okay, Hannah, that's a very good, very interesting talk. I'm wondering whether your methods of symmetry for solving nonlinear differential equations are closer related to those for solving linear, like for example, the Laplace equation and the Helmholtz equation. I've been working on that. I'll be talking about such solutions this afternoon.
I mean, there may be some connections. I don't know of course, your method yet. We'll be listening to the talk, but the general problem is that for linear equations, we at least sometimes have a method of solving them. For nonlinear, the only method is basically guessing the form of solution. All the methods that we know from nonlinear differential equations is starting from a guess, and the symmetry produces a good guess to start with. And yes, I'm looking forward to your talk.
Thank you.
And one more question from Guillermo Morales Luna.
Yes, I would like to ask whether the quantum codes are just relevant for information representation, or are they used in a special way in your processing?
Excuse me, quantum what?
The quantum codes.
Oh?
Code.
I think codes.
Oh, code. Yes. If you mean quantum computing, no. This is not a direct application of quantum computing. The only part of quantum computing was that most quantum computing codes are in fact, error correcting codes. And they, of course, we can simplify them tremendously if the states, quantum states, are error protecting. But as far as I know, and my current research, at least for 10 years, is totally not connected with quantum computing. So I'm not current in the literature, but as far as I know, the states proposed by Zanardi and Rossetti were never implemented in hardware.
Okay, thank you.
Okay, we have one more question from Gregas Kozan. Gregas, can you unmute your microphone? Maybe we have some difficulty.
I'd like to make a question. I congratulations you for your excellent presentation, Hannah, and open a big number of questions to us. But I was thinking in the Penrose tiling and the forbidden symmetries. It is possible to use these methods that you present for this problem, and how you can implement in that.
Well, I would like to work. This is a good question, but I would like to work with the problem and think about it. There's no immediate solution.
Yeah. Okay. Thank you. Thank you very much.
Okay, Gregas, are you able to communicate?
Please send me, if you would like to send me a written version of the problem, and maybe some statement of the problem. I would be happy to
okay, thank you. I'm going to send it. Thanks.
Okay, I think maybe we could thank Hannah for the presentation and move on to the next speaker. Hannah, I guess that's your job.
I need to change the screen. So could you announce the next speaker, because I don't have the schedule. I still have my presentation.
Yes, no problem. The next speaker is Daniel Brezov, and he will speak on the order of finite generation of SO3 and optimization of rotation sequences. Daniel, please continue.
Yes, that will be me. Thank you very much. Can you hear me?
Entonces hay que cambiar la presentación de Hannah.
Yeah,
¿no?
to disable your screen share, Hannah. Yeah, thank you. Daniel, we continue.
Okay, so it's me then. Okay, let me just share the screen and probably. Okay.
After you share your screen, you might want to disable video because you seem to have some delay.
There's a delay in the connection. Okay, sure. Yeah, something's not working properly. Okay, now stop the camera then. That's not good. Okay, let me just say, use this
So
time to
far, I
say,
see only a blank shared screen. Yes, now it's correct,
that's
but
correct?
not in
Okay.
presentation mode.
Okay. Okay, thank you. So, first of all, let me say that I'm grateful for having this opportunity to honor Professor Ugiewicz. He's been an inspiration for me as well, although unfortunately, I got to know him during the last years of his life. Now, what I'm going to talk about is perhaps a simple thing compared to other talks. It concerns one group that has been studied for a long time. We know perhaps everything about the rotation group in 3 dimensions, and of course the unitary group, which we use also unit quaternion using quantum mechanics. But there are always new things or new ways to approach things which are practical and good for the application. And one thing that was interesting for me was the so-called order of uniform generation or finite generation of the rotation group. I would say, cite an old result due to Lowenthal. Let me show you. So, what is the order? The way he defines it in the context of rotation group is that you have 2 elements or 2 axes of rotation, or it's better to say 2 planes of rotation. And what is the minimal number of rotations in which you can decompose any element in the group with respect to these 2 planes? So it's similar to the Euler, classical Euler decomposition setting. So if the 2 planes are orthogonal, the length is 3. So you say the order with respect to these 2 elements is equal to 3. If the angle is different, so as you decrease the angle between the planes or the axis of rotation, you actually increase the minimal number needed, the minimal length of words in which you can represent any element of the group. So, Lowenthal came up with this formula in the 70s. And this very simple formula, gamma, here is this angle between the 2 planes. And unfortunately, he used very, very complicated mathematics, advanced calculus, and geometry to prove this result. So, even though the result is simple, it's very difficult to explain this result to first-grade students, for instance. It could be difficult even for specialists to follow the proof. So my goal was to aim for a simpler proof and perhaps more general results. We can take, for example, instead of 2 planes, we can take 3 planes or more planes and see what happens. So first of all, this is not just for fun. Well, fun is the most important reason, of course, we do mathematics for, but it is interesting also for the application. And 3-dimensional rotations are applied, in many advanced areas, not just in kinematics, but also in more advanced areas of, or let's say more up-to-date areas of research: robotics, navigation, computer animation, and tracing, a lot of things. The other reason is to make things more accessible, of course, simplify, and see how this relates to optimization problems. I've had the opportunity to study optimization problems for example, for spacecraft and aircraft navigation when you have small number of rotations in the composition. For instance, if you introduce a fourth rotation instead of the usual number is 3, of course, but with the fourth one, you have an additional parameter. You can use this parameter to optimize. And of course, with higher number, you have more parameters you can optimize numerically, for instance. And of course, this all relates to the SU2 group, which is used to in quantum computation, for example, related to qubits. And also, I'm going to mention in the end of this talk, it relates to also to inhomogeneous Euclidean transformation. With it's easy to go there using the apparatus of dual quaternions, dual matrices, and so kinematics, but done, in a simple way with the dual algebra. Now, to cover all these things, and of course, there's a non-compact version, which I'm going to just. This is a three-dimensional Lorentz group, which is closely related to the rotation group, and many things are. For many things, you can follow the analogy, but there are differences. It is non-compact. It has more complicated structure. So I'm not going to obtain any particular result, just say what the problems are there. But to cover a broader area, I would define this order generation a little bit in a broader sense, not just two elements, but let's say we have some set of subgroup, and I'm gonna use a billion subgroups, so one-dimensional. Because when you study rotations, it's easy to talk about axis if you're in 3-dimension, or planes if you're a higher dimension in the decomposable case. But if you want to talk about unitary transformations, this doesn't make sense. So it's better to talk about orbits of the S1 in the group, in the sphere and the dimensional sphere. So you have something like Hopf vibration, and so every abelian group. So fixing a rotation axis in the SO3 case, SO3 case, is equivalent to fixing an abelian subgroup in the quaternion case. So with this little bit more abstract definition, we cover both cases. So the order would be the minimal number in which you can decompose minimal number of factors, in which you can decompose every possible element of the group with respect to this subgroup. So picking elements of this subgroup. So for instance, as I mentioned already, composition is 3. When you decrease the angle, it becomes less. Now, let me continue. Yes, by the way, I forgot to mention this means rounding. So these brackets here mean rounding from above. So it's not the usual integer part, but it's rounding from above. And one more thing, so one more way to generalize this result is, let me mention Hamada in 2014 used such an idea, but to study particular elements for the group or subsets of the group. So let's find the order, for instance, or a subset of group elements given by some restriction on the angle or the axis of rotation. This is also a meaningful and very practical direction of research. So we had in the same year we had some study done with the colleagues from the Academy of Sciences. I'm going to mention this in a while. So let me give you a very brief tour of what I've done here. So these are the notation. This is the notation. Gamma would be the relative angles between the axes. Beta would be angles between the compound rotation axis and the corresponding axis in the decomposition. And this gamma tilde would be the inverse cosine of the matrix elements of the compound rotation in this basis. Is not a basis, but let's call it a basis of rotation unit vector. So in the decomposition, so it's a for instance, tilde gamma 1 would be the distance or the angle between the initial axis and the axis after rotation acts upon it.
Excuse me, we are losing your voice. Try to speak very slowly because acoustic is not in your favor.
Oh, is it just acoustic or there's some problem with the connection, internet connection?
It is I think acoustic because
okay just
now you are here clearly and sometimes
thank you. I try to speak closer to the mic. Maybe that's the problem. Okay, so after introducing notation, so I'm going to speak about in terms of angles, or which is the same. We can talk about we can talk in terms of spherical distance, because these rotation axis, they of course representatives of two-dimensional projective space, but locally we can take patches on the unit sphere, so we can talk about spherical geometry. So locally it is the same, and what I call angle between two axes is smaller of the two, of course, if they're not equal. So this, in terms of trigonometry, this simplifies the consideration. So first of all, my strategy would be to reduce this complex. Complex, to substitute the complex treatment of Lowenthal and Hamada with a series of very simple lemmas and theorems, and even generalize their results. So first of all, we have some inequalities for these shift angles. So phi is the compound rotation angle, gamma ij are the relative angle between the axes, and with tilde it means that one of the axes is shifted by the compound rotation. So we have in the low dimensional case, so low order cases, we have these results. So this first one would be helpful by the end of the study. This is a result for decomposition into two factors. By the way, this is the Rabi resonance condition. It is in quantum computation. It actually could be seen as a condition for decomposition into two factors. So we have a coincidence of two angles. So for two factors, for more factors, we will have inequality rather than equality, but for two factors, of course, the number of parameters is smaller than the dimension of the group. So we have a restriction of degrees of freedom, so to say, reduction of degrees of freedom. So, my study concerns more than two factors. We start with two factors just to make everything, more consistent, but the inequalities there would be for more factors. By the way, they hold also for two factors, but they are not sufficient. So we have an additional restriction based on the fact that dimension is 3 and we have only 2 here in the decomposition. So, for three factors, which is the classical case, we can write the decomposition condition as the condition for positive or non-negative definiteness. Sorry, of one determinant. This determinant actually is the Gram determinant for the system of vectors which moves along. So if you think of this as a transformation of rigid body, we have a fixed laboratory frame, and we have a frame which moves along with the body, with the rigid body. So this would be in the fixed frame. This would be the representation of the Gram determinant of the so-called moving frame, and this is actually a condition for the existence of such a frame. So we have a very easy way to represent the solutions. This I've done with the colleagues in 2014 as well. But for now, it's not important. What's important is to consider the geometry of this condition. So this is the Cayley nodal cubic, which represents the inside of this shape is the domain in which things are decomposable. Outside of it, they're not. And in the more general condition for three factors is given by this inequality. So, the thing is that we have both upper and lower bound. So one way to get rid of the lower bound is to say that first and third axis coincide. Then it becomes trivial. Or another way is to say that at least the angles between the angles each of them makes with the second one are equal. So this would be two easier cases. So for three factors, we have similar representation. For four factors. This is the result from, I think, 2015. We have similar conditions. The only thing here is that it's not as general as the three-factor thing. We have one of the axes reappearing twice, and depending on the order, we have different conditions. But always we have condition for the the condition is related to the path of so this is broken geodesic, starting from the first axis and going to the last one. And the length of this geodesic would be the right-hand side of this equality in each particular case. And the idea is that we can generalize this for more factors. Now, this perhaps I will not explain this picture because I will run out of time. So this is just an illustration of the simplicity of the proofs in low-dimensional cases. So we have intersection conditions and relations for radius of better not explain it, because if I have to do it, I will have to spend some 5 minutes here. But the things we use in this sort of group is triangle inequality and intersection. So the most basic things we can use in geometry. Now we can talk a little bit about distance on the sphere. I use Rodriguez's formula, but also the Haversine distance. They give you the same thing. Now, so the idea is that sometimes we have different representations of rotation. It could be axis angle, it could be matrix. So depending on which is more convenient, we can use the inequality for the axis and angle, or matrix element, or angles which come from matrix element. But sometimes also we cannot say what the corresponding axis, where the corresponding axis is, or what the corresponding angles is. So we can consider restrictions on either one of those. So this is the next theorem. But we're still in a low-dimensional case, and I'd like to move forward. Now, next argument is induction. So again, things you can use to convince first-grade students, or maybe advanced high school students. So that was the whole point. So we can extend this result that the compatibility condition is given by estimate which involves the length of a broken geodesic going from one axis to the other, the axis being points on the sphere. In this case. So this sort of argument gives you a lower bound for the minimal number, or what we call the order of the rotation group, for a particular element of the group. Okay. Now, so if you want to make it for any element, of course you need to take the maximal value here, because we don't know anything about the group element here. We need to be prepared for the worst case scenario, which means pi over gamma. Gamma bar would be the average distance between two points in this broken geodesic. So we easily recover Lorentz result, but we aim for more here. We aim for instance, so there are different ways to represent estimate, imposing certain restriction on either the angle or the axis, and there are easier settings. For instance, one of closed rotation, so starting and ending with the same axis, and one which is only having two axes. So, or at least if the relative angles are equal, this simplifies greatly the calculations. But if we want to consider two axes, we can use this lemma for that. So, yes, if with two axes we either begin and end with the same one, or the one next to the last is the same as the first. So we have either of these two cases. The lemma is more general, but the two-axis setting is a particular case. So this gives you an opportunity to also consider infinitesimal or smooth transformation, which is good interpolation problem, for instance. So we start, we follow a path on the sphere, and this means that the composition axis is the smooth set of composition axes, which are mapped at the points on this path, the smooth path. Yeah? And now the initial and final points on this path are associated with the first and last axis. And we have our broken geodesic now becomes smooth geodesic. For instance, for a closed path, we have a simple formula. D is on the left-hand side. D is not differential; it's the distance between the first and the last. Sorry, not the first and the last, but the first and the map of the first under the compound. So we can use this stuff also for interpolation. And it's interesting that some of these things, I realize that I have about 5 minutes, so I'm going to skip some slides at the end. But just to mention that there's a relation between these things and some classical theorems of mechanics due to Duncan and Ludwig Hamilton. And of course, we can lift up this whole construction to the spin covering group, talking about unit quaternion, using the axis angle representation and this the scalar product, the dot product. So we can, everything we've done here, we can translate into the quaternion language and using quantum computation, for instance. As I mentioned, we can do this stuff also for the whole Galilean group, so for rotation and translation. It's a very interesting theory, by the way, using dual quaternion and displacement dual axis, but I have to skip this. And it's interesting to see how this relates and what problems we have to make this happen for the three-dimensional Lorentz group. It would be also very practical because it is used, for instance, in a quantum scattering, monodromy matrix approach in quantum scattering, and the direction of the idea of axis direction has some meaning there, physical meaning in terms of scattering potential, which only transform the phase or which don't change the phase rigid one. So it would be interesting, but the structure of the group is different, and it would need a kind of different approach. So I'm gonna save this for later. And thank you for the patience of listening to my talk, even though it was there were some technical problems. If you have questions or comments, especially comments, I would be glad.
Thank you very much.
Could you show the slide with the references to your papers again? It was 2 or 3 slides back.
Sure. So here is.
Yes.
This is about the dual. This is about dual quaternions and dual matrices, and the other one is about embedding the three-dimensional thing into high dimensions. It uses some techniques from twistor analysis, but it's mostly projective geometry tricks. Yeah, it might be interesting for you. I don't know.
Thank you.
Yeah.
All other questions, please contact the speaker offline, because yes, but we are already on time for the next talk. So Bill, you've shown that you want to ask something. If not, please, Bill Page, please contact the speaker offline.
Yes, I'm sorry. Yes, I wanted to comment to the presenter regarding a message that appears on his slides that seemed to be a window behind his presentation screen. It says, please move this window away from the shared application. Perhaps that's a problem related to why you are having communications issues.
I did not realize.
Okay.
I did not realize it was visible. Sorry for that inconvenience. I thought I was the only one to see this. I'm sorry. You should have told me earlier to deal with this. Sorry about this.
Thank you. Thank you. Let us contact the speaker offline. Please send him all other questions. We are going to the next talk by Varsha Aishvara, Siyam Prasad Kuncham, and Baburshi Srinivas Kadukodi. If I mispronounced any of the names, I apologize. The topic is path, norms, and matrix. Please connect your slides.
Good morning, everyone. I would like to share my screen.
Yes, share screen. This is in the path on the bottom of your screen, the green one. Yes, we see your screen.
Yes. Is it visible? Okay, thank you.
Yes, it is. And we hear you.
Is it visible now?
It is well visible. Thank you.
Okay, thank you. Good morning, everyone. I'm Varsha from Department of Mathematics, Manipal Institute of Technology, Manipal, India. Topic of my presentation is path norms on a matrix. I would like to thank International Conference Applied Category Theory, Graph Operand Logic for giving me this opportunity to present my paper here. These are the contents of my presentation. To begin with, we give the norm ring definition. That is, let R be associative ring. A norm on R is a function satisfying the following properties. And seminorm on a matrix, let M be a set of matrices with entries from the normed ring. Then this real valued function, if it satisfies the following properties, we call it as a seminorm. We define path seminorm on a matrix. Let R be a normed ring and A be a M by N matrix with entries from the normed ring R. We define binary row path seminorm on A, given like this, where it is a maximum of absolute sums of AIJs, where those JIs are satisfying these values, these conditions. In detail, I would like to explain it with an matrix. So basically, we collect all those paths from where we take each element from a row, and the next element will be either exactly below it, that is from the same column, or from the diagonally to the right of it. So we collect all such paths and we take the maximum of it, maximum of the absolute value of the sums of it. So the brute force method is that to get the maximum of it. But we see that there are in total 2 to the power mn paths possible in this matrix. So which means, and we have to find the maximum among them. So which takes exponential time. So we give algorithm to compute the binary row path seminorm on a matrix, and that we will see that it is much more less than the exponential, which takes much more less time than exponential. Right. So what we do is we compare the sums of absolute values are the sums of only the two ones. That is, for the second row, we add this minus 34 with minus 71, and whatever the sum is there, minus 105. And similarly, we do it for minus 102 and minus 171. When we get minus 173, now we take the maximum of this sum, that is minus 173. We just take the maximum of the absolute value of it, and we update this by minus 173. The ones those are with the thick lines, those will be updated for the second row. And similarly, we repeat this step for the first row, and we do it, and we find the maximum absolute value in the topmost row, which is nothing but the binary row path seminorm on A. And here we see that for every element here, we have exactly one comparison done. So for except the last one there is no comparison. We just add them and keep it as it is. So in total, we can see that in each of the n-1 row columns, we have one comparison, and such m-1 rows we have. So in total, the time complexity of this algorithm is of the order n square, where n is the maximum of the size mn. These are the different binary path seminorms on a matrix. That is, we need not have to compute always from comparing from the last row and go to the first. We can also start from the first row and go to the last. We need not have to have always path from which is diagonally on the right side. It can be on the left side also. So such 4 different ones we'll get when we go through the rows. And similarly, through the columns, when we go, 4 such are possible. So we tabulate them in this form, and we can see that these 8 ones, which we are 8 different ones we are getting, we can compute them using the same matrix when we have only one among those 8. So this matrix gives, this table gives that. And we observe that when we compute, though the way of computations are different in 8 different types of path seminorms, but ultimately what the solution we get, that is the path seminorm and as well as the path. They coincide in this case, R down arrow, R and R up L. So out of 8, we are getting 4 distinct ones, and they are tabulated in this way. We define path norm on a matrix. Let R be a norm ring and A be a matrix with entries from R. We define binary row path norm on A, which is the maximum of path seminorm on A and the column norm on A. We see that the norm which is defined is satisfying these following properties. That is, non-negativity, definedness, absolute homogeneity, triangular inequality, and compatibility with the vector norm. And earlier case, we have seen either we take the element which is diagonally to the right or to the left in each case. But we can also have the paths both from left side and right side also. So in that case, we get still more possible paths here. So it can have a zigzag path also. And that path, we should remember that each element should be from, there should be one element from each row if we are traversing from the first row to the last row. And the column, the next element should be either right below it or to the right or to the left of it. So for the first one and the last one, there will be only 2 possibilities. But for the all the columns in between has 3 possibilities. So the brute force method will take will give the total of 3 to the power mn possible paths, out of which to compute the maximum will take exponential time. So we give the ternary path seminorm, which is somewhat similar to that of the previous one, which we have given for the binary row path seminorm. This is the algorithm. And since for each element, except the first and the last, we have two comparisons. And for the first and the last, we have one comparison. So it goes, the complexity computation also goes along with the of the binary row path seminorm, which is again of order n square, which is where n is maximum of mn. In this case, we see that the sorry, this is ternary. There's a type mistake here. So this is ternary row path seminorm on A. Here we get it as 325, which is obtained by the path 129, 76, and 120. And we denote the one by R down arrow LR because we are comparing from the both left side and the right side. And if we traverse from through the columns, then we give it by C right arrow UV. As in the case of binary path seminom, we have 8 different ones. Here we have 4 different ones. Again, in detail, if we see, we get that there are only 2 of them. Either they are traversed from through the rows or through the columns. The condition number of a matrix for a non-singular square matrix, the condition number is given as the product of norms of the matrix and its inverse. Now, here is an example in comparison with the row norm and the path norm on a matrix. So we can see that both are having a closer value. In case of diagonal matrix, it is slightly away as 4.5 and 2 are slightly, they are away. What happens is when we come from the matrix to any general matrix to the diagonal matrix, this difference is increasing. So we give the weighted path norms where we give weights for the path norm of the matrix and the matrix norm. And when we give the weights, we may have to give the weights accordingly to the type of the matrix that we are computing. And we see that the path norm that we have defined satisfies the following properties. That is non-negativity, definiteness, absolute homogeneity, triangular inequality, and compatibility with the vector norm. These are the references. And I would like to thank the organizers of International Conference Applied Category Theory, Graph Operand Logic for giving me this opportunity to present the paper content here. And I would also like to thank Manipal Institute of Technology, Manipal, Academy of Higher Education, India for providing me Dr. TMFI PhD scholarship. And thank you all for your attention. Thank you.
Thank you. We have a lot of time for the question and discussion. And first, I want, of course, to thank the speaker for this talk, and also in the spirit of, as it was mentioned before, this is very intense conference, and we have a lot of talks, and we all want to be totally focused, but sometimes it is difficult to remember everything. If you could summarize the main thesis of your talk in a couple of sentences, which will make it easier for us to remember.
Okay. Here we define path norm on a matrix. So what we do is we find the path by taking each value from a row through the matrix, and we add them such that the sum of them, its absolute value, is the maximum. So there are 2 different types of it. There is binary one and ternary one. So binary one, we have only option of adding the element which is right below it, or just right to the diagonal right of it. In the ternary one, there are 3 options, either to the left of it, to the right of it, or to the below of it. So basically, it travels through the every elements of the matrix, and it says that how far or how the elements of the matrix are dispersed in the matrix. So we are still working on it. So this is one of the phase where we have reached to this point.
Thank you. Thank you. Bill Page, you have a question, yes? I encourage also yes. Other questions. We have a lot of time.
Yes, I have a question of the speaker. I was wondering, if you could explain what is the application of path norm, like what is the purpose for doing this calculation?
We were trying to find the condition number using the path norm, whether it can say how well conditioned or ill conditioned matrix is. So we are just we have just started to work on it, and yeah, that's the idea what we have thought of and come to this point.
So could you say that it is related to questions of numerical stability or something of that sort?
Yes, sort of that sort.
Okay, thank you.
Thank you.
Do we have other questions? If not, we are thanking the speaker, and this is the question to the main organizers. Are we going now to the next talk, or are we having a break?
If there is one more speaker in this section, we can go ahead with the next, please.
Okay. So the next talk, I hope the speaker is already connected. Let me know.
Okay.
I think you must unmute or unshare the screen. Yes, thank you.
Okay. So let me announce the next talk. Sayam Prasad Punsham, Tapakis Sahu, Babushari Srivantas, Kadukoni, and Harikrishnan Panakal. My deep apology, I probably was terrible with the names. I tried the best I could. The title is on absorbing ideas of N groups. Yes, please, you have the screen.
Yeah. Good morning, everyone. Are you able to see my screen? Are you able to listen my voice? Could you please clarify?
Yes, we see your screen.
Okay. Audible to everyone, or can I raise my voice, or is it okay?
We hear you very well.
Okay. Thank you. First of all, I would like to thank the organizers of this international conference, Applied Category Theory, Graph Applied Logic 2021, in the memory of Professor Jibjig Wojcik. Okay, difficult to pronounce the name. Okay, anyway, thank you very much. And the title of my talk is on absorbing ideals of N groups. So, in this talk, we consider gyrosymmetric right near ring N as a generalization of a ring in which addition need not be abelian, and we assume only one distributive axiom. So we assume right distributivity axiom. Therefore, we call sometimes as a right near rings. And we define I2 absorbing ideals where I is in 0, 3, E of an N group as a generalization of prime ideals defined by the authors. We provide suitable examples and prove some properties, and also study the interplay between the prime ideals of a near ring and those of matrix near ring. And we extend the relations to absorbing ideals and establish one-one correspondence between the absorbing ideals of N and those of a matrix near ring over N. So there are some key terms in my talk. One is near ring N group, Insertion of factors property, prime ideal, completely prime ideal, 3' ideal, matrix nearing, and monogenic. So before going to the actual results, there are some preliminaries here. Filch from the reference book, from standard notations and the symbols preliminaries, we use this filch. A right nearing is an algebraic system in which n is an additive group, not necessarily abelian, and multiplicative semigroup satisfying only one distributive axiom. X plus y into c is x c plus y c for all x, y, c in n. And this is referred as right nearing. And in ring case, we have 0m equal to 0m, 0 equal to 0. But here we have only 0m equal to 0. And a minus m into n is minus mn for all mn. But in general, a into 0 is not equal to 0 for some a in n. So if at all this condition true, m into 0 equal to 0 for all m in n, then n is zero symmetric. In this case, we denote this as n equal to n. So in general, this condition do not hold, but sometimes we may assume this condition for some of the results when you generalize from ring to a near ring. For a group G, not necessarily abelian, the natural example of a near ring is consider the set of all maps, write it as mg from G to G, and determines the structure of a near ring, which is not a ring. And here we consider the pointwise addition and function composition. So obviously, for some appropriate group G plus, every nearing can be embedded in MG, the set of maps from G to G. So this is a natural example of a nearing. And ideal, a subgroup A plus of n plus is said to be an ideal if it is normal. An is subset of I, and n into n1 plus a minus n, n1 is in A for all n1, n belongs to n and a belongs to E. And like in module over a ring, we have a structure of near n group. So this is a group action of a group over a near ring. Instead of a ring, we will consider a near ring. So therefore, there is a mapping from n cross G to G, where G is a group and n is a near ring. And the element xg is written as xg, satisfying the conditions x plus y into g equal to xg plus yg, xy into g equal to x into yg for all g belongs to g and x comma y in n. And it is evident that every near ring is an n group over itself. Also, each module over a ring is an n group. Sometimes we write n group as G left suffix subscript capital N, because n operating from left side. Okay. So ideal of an n group is defined in this way: normal subgroup satisfying the condition x into G plus a minus xg belongs to a for all x belongs to n, a belongs to a, and g belongs to. As in case of rings and modules, here also we have module homomorphism, very similar one here, n group homomorphism. So additive condition here, linearity, and also h into n a equal to n h a. So other definitions include, one is the distributivity, because in general in near rings left distributivity law do not hold, but if in case for any set of three elements here, x into a plus b equal to x a plus x b, in that case x is a distributive element, and n is distributive means if it is true for all the elements, then we call it as n is distributive. And this definition is well known even in the ring case. A proper ideal P of n is called prime if for any two ideals S and T of n, the product ST is contained in P implies that one of that is contained in P. And completely prime, then call it as C prime. Whenever the product ST belongs to P, then one of that S or T belongs to P. So in case of commutative rings, all these primes will coincide, completely prime, all will coincide. But in case of near rings, all these are different due to the non-abelian property of group, and also one of the distributivity fails in this case. And an ideal A of G is said to have insertion of factors property. Denote this as IFP. If X belongs to N, G belongs to G, and whenever XG is in A, then XNG is in A for all N belongs to N. And here 0G is an IFP ideal, then we call G as an IFP N group. That means 0 is an IFP ideal. And some review of literature of our work, a natural generalization of module over ring is module over arbitrary near ring, and precisely it is a group action of a group over a near. And Jiglal et al. Studied in this paper different R prime ideals appeared in algebraic vacuum. Generalized prime ideal in module over rings to module over near rings in several ways. They obtained some characterizations of prime near ring modules and exhibited interesting properties. More importantly, connections between prime ideals of module over a near ring and the corresponding annihilators in near ring were investigated. And in 2007 course, much before this, on absorbing ideals of commutative rings. So Badawi introduced the idea of two absorbing ideal of a commutative ring with identity as a generalization of prime ideal in a commutative ring and explored some properties. And later, Dharani and Sohenia, two absorbing and weakly two absorbing modules studied in some paper, and Grunewald and Yan in the paper non-commutative two absorbing most modules over non-commutative rings in the Electronic Journal of Algebra. We studied generalized generalized two absorbing modules over non-commutative rings. So as a whole, there are many papers appeared in case of rings generalizations in terms of absorbing ideals, but in near rings recently started. So we have obtained few results on this. So these are the some literature on this work. I have referred these papers, of course, in the references I have already listed, but time being I skip this on and then go to the main content. So throughout we use N stands for a right nearing, as I said, and G stands for N group, and all the further undefined notations and conventions will be as in the book Pilch by the title is nearings. Now we start with the definition of completely two absorbing ideal. This generalizes C prime ideal of a near ring. An ideal I of N is called completely two absorbing ideal of N if whenever you have X, Y, sorry, here misprint it's a Z in N, whenever the product X, Y, Z is in I, then X, Y is in I, or Y, Z is in I, or X, Z is in I. And N is called C2 absorbing if 0 is a C2 absorbing ideal of N. So Jiglal defined this prime ideal of an N group, and the generalization is that a proper ideal P of N is called strictly completely prime whenever if the product XG belongs to P implies X ideal generated by G is contained in P or G is in P. And every completely prime ideal is strictly completely prime, and converse need not be true in general. So we have the simple two lines proof, and we have provided examples to justify this converse, not true. Next, an ideal I of Z, N group G. G stands for N group here, or a module over a near ring. So to be completely two absorbing ideal if whenever X, Y in N and G belongs to G, the product X, Y, G is in I, then X, Y is in the annihilator or the Noetherian quotient of I and G, or xg belongs to I or yg belongs to I. And here an example of an n group, we take Z8 and then thing of integers, of course, G is an n group. Then I1 is 0, 4, I2 is 0, 2, 4, 6, and ideals of G. It can be verified that I1 is C2 absorbing ideal of G, but not C prime, because of 2 into 6 is in I1, but neither 2 into Z8 is contained in I1 nor 6 is in I1. And the ideal I2 is C prime as well as C2 prime. So it can be both. So referring the near ring N, given in the table of nearings book E23 page 4.408, if you consider this nearing with this table multiplication and addition, then n is not zero symmetric because the condition n into 0 need not be 0. And here 0 is C prime and 0 C2 prime, C2 absorbing also. And there are some similar examples wherein it's not C prime but C2 absorbing. And further we have an example M equal to 2 by 2 matrices with entries from Z2 and N equal to M to Z. Then G is an N group and I is an ideal of G, which is C2 absorbing but not C prime. And still we have an example S3 nearing given in the table H11 of Pilch book, which is not zero symmetric and non-commutative. And n over n, if you consider nearing, where the multiplication is defined in this way, addition and multiplication, then here also 0 is C2 absorbing but not C prime. And let us see how homomorphic images of this C2 absorbing ideal. Let H be an n homomorphism of n groups G onto G dash. If A is a C2 absorbing ideal of G containing kernel H, then HA is a C2 absorbing ideal of G dash. I'll skip the proof because it's a verification. And H is G to G dash is an epimorphism, n group epimorphism. A dash is an C2 absorbing ideal of G dash, then H inverse A dash is C2 absorbing ideal of G. And we have the definition of for any ideal, A is to G is the Noetherian quotient. So whenever A is an ideal of G, A is to G is an ideal of N, like in module case, same. And here, if A is a C prime ideal of G, then A is to G is a C prime ideal in N. If A is a C prime ideal of G, then A is C2 absorbing ideal in G. Because there are routine verifications, therefore I skip the proof. And as in Pilch 28, the reference, and group G is monogenic if there corresponds an element G in G such that Ng equal to G. This is very similar to a cyclic group. This here G, we call it as a generator for this N group. So that means for every element of G, you can write as a product with element in N and the element G. Then we call it as a monogenic. When from Key and Mayer, matrix nearings and zero primitivity in Montas journal, G is called locally monogenic if every subset S of G, where S is infinite, there corresponds an element A in G such that S is subset of N. And every locally monogenic N group is monogenic. And I have a note here, let A be an ideal of G, and then A is to G is contained in A is to small g for all G belongs to G minus A. Let G be monogenic by G, element G, then A is to G equal to A is to Z for every A of ideal A of, in case of monogenic. We have a theorem here. Let G be a monogenic and A be an ideal of G. If A is to G is a C2 absorbing ideal in N, then A is C2 absorbing ideal of G. So I'm skipping the proof. And referring to this Meldrum nearings and their links with groups, Pittman publications, we say that N is distributive over G if D into G1 plus G2 equal to D G1 plus D G2 for all D in N and G1 G2 belongs to G. If G is locally monogenic and N is distributive, then N distributive over G. Let A be a C2 absorbing ideal of G, where G is locally monogenic over a distributive nearing N. Then A is to G is a C2 absorbing ideal of I just skip the proof because it's not necessary here. And you say that a N group is connected, N group G is connected. If for any G1, G2 belongs to G, there exists an element G in G, and elements U, V in N such that G1 equal to U into G and G2 equal to V into G. So in this case, we say that N group is connected. Yes, a corollary here, G be a connected N group over a distributive nearing. If A is C2 absorbing ideal in G, then A is to G is C2 absorbing ideal in N. Let G be a monogenic over a distributive nearing N. If an ideal A of G is C2 absorbing in G having IFP, then A is to G is C2 absorbing ideal in N for all G belongs to G minus A. And, let P and Q be ideals of G with Q is contained in P, and P is C2 absorbing, and only if Q over Q is C2 absorbing ideal of G over. And if you consider zero symmetric nearing and C2 absorbing ideals of modulo over a zero symmetric nearing, in this case section, we assume that n into 0 equal to 0, basically, and we have certain examples for C2 absorbing ideals which are not prime. So these are all if you take n as Z8 and G as D8, the integral group of order 8, and define an external operation in this way, and reflections and rotations. In this case, also is C2 absorbing but not prime. And similarly, we have an example D8 over D8. In this case, I is C2 absorbing but not C prime. I equal to E comma sigma square, which is C2 absorbing but not C prime. The reason is given here. Next, we provide the notion of a symmetric ideal, which is analogous to the notion defined in the Lambeck lectures on rings and modules. An ideal A of G is said to be symmetric if for A, B belongs to N and G belongs to G, A, B into G is in A implies that BA into G is in A. In this case, we say that it is symmetric ideal. And if N is commutative, automatically this N group is symmetric. And let G be an N group where N is zero symmetric. If A equal to A1 intersection A2 is symmetric, and then AIs or C prime ideals of G, then A is C2 absorbing ideal of G. And consequently, one more theorem here, A be a C2 absorbing ideal of G, then A is to G is C prime ideal of N, implies that A is to G is C prime ideal of I think here print mistake here, C prime ideal of G here, then A is to small g is A. Yeah. So next, let us in the final section of the presentation is the prime ideals in MNN group NN. So we now review some basic definitions about the matrix near ring from the paper Matrix Near Rings are Tudor Mathematics, first appeared in 1986. For a zero-symmetric right near ring n with 1, let n power n denotes the direct sum of n copies of n plus. And the elements of n power n are referred as column vectors and written as R1, R2, Rn. And we have two natural injection and natural projection maps. The symbols ij and here I suffix I, ith coordinate injection and jth coordinate projection maps. So for example, for an element A in n, the ith injection is in ith place we have A, and jth projection is in the equal to pi j of A1, A2, An is Aj for any interpole in Nn. So the nearing of n cross n matrices over n denoted by the symbol mnn is defined as the subnearing of m n power n. So m n power n stands for set of all maps from n power n to n power n generated by set of functions fij to the power of r from n power n to n power n, where r is an element of n and I from 1 to j. So if you want to define this fij r at r1, r2, rn, it is some s1, s2, sn, where in the ith place r into I rj and the rest of the places sk is 0 for k not equal to I. So you have a composition of the projection map and map fr from n to n, and I think injective map, if you take composition of all these three maps, then we write this as fij power of r. So if n happens to be a ring, then fij r corresponds to n by n cross n matrix with the rth position, r in the ijth position and zeros elsewhere. So we have some here some differences. Now if you take an ideal of n over n, the corresponding ideal I star star is in MNN group NN. It is obtained in this way. A belongs to n, where A is pi j a for some A in I, and n power n becomes an MNN group here. Means over the n power n is an abelian is a group, and over the matrix nearing MNN. Therefore, this becomes MNN group NN. So therefore, now we will see the interplay between these two. Just for idea, just I'll show some results here. IIT is ith tuple, and ideal generated by IIT is the T00 and so on. And for completeness, we give this. And here, if you define this, I is an ideal of Gi, and Ng is not contained in I. Then I is 3 to absorbing. If AB and G is contained in I, then ABG contained in I, or AG belongs to I, or BG belongs to I. The same one, if we extend this to MNN group n power n, then the definition is I is C to absorbing. If AB belongs to MNN and rho is in NN, AB into rho is in I, then AB n power n is contained in I, or A rho belongs to I, or B rho belongs to I. So with this, what we is here, if I is C2 absorbing ideal n over n, then the corresponding ideal I power n is C2 absorbing in MNN group NN. So this is the between n over n and the corresponding matrix nearing n over n power n. Sorry. And similarly, if I is C2 absorbing ideal in MNN group NN, then what about in the n over n base nearing? So that we define it as I star star. So ultimately we will get 1-1 correspondence between, I'll show it here. Yeah. there is a 1-1 correspondence between the set of I2, where I from either C prime or 3 prime absorbing ideals of NN, and those of MNN group NN. So if we write P as the set of all ideals of N, where I is I2 absorbing, and Q as ideals of N power N over a matrix nearing MNN, which is I2 absorbing, then we define here phi from P to Q by phi of I equal to I power N. Then by these two theorems, phi of I is I2 absorbing, and conversely, if you define psi from Q to P by psi of I equal to I lower star star, then by these two theorems, phi of I is I2 absorbing. So therefore, pi circle psi at I is an identity map, and psi circle phi is an identity map in N, whereas the first one is identity map in MNN. So therefore, P and Q are isomorphic. That means we got the isomorphism between the set of absorbing ideals of N over N and the set of absorbing ideals, two absorbing ideals of N power N over the matrix nearing MN. So this is the entire work, and acknowledgements to our university, and there are some references of this work. I thank once again the organizers for giving me this opportunity. Thank you all.
Hello. Well, thank you, speaker.
Yes.
I think this is the last talk of this session.
Yes, is the last talk in this section. But if there is some questions.
I think I can ask one question at least,
Yes.
although it's of a more general nature. I was wondering if you could outline the reason why the study of near rings has become so popular in recent years.
Yeah. Because it is a natural generalization of a ring. A ring admits the linearity property, but wherein near ring we do not have a linearity property because of the distributive property fails here. Only one distributivity is assumed. So ring, therefore, a set of all group mappings, if you consider from group to group, which is not necessarily a billion group, and then that forms a near ring, but not a ring, with the usual composition of mappings and the usual addition of mappings. So therefore, from ring results, if you want to generalize to near ring, these are extremely difficult, and this handles different nonlinear phenomenon and algebraic systems. So that is one idea. And because of these substructures, in case of rings, we have just an ideal. But whereas when you go to near ring, we have substructures are different again. N subgroups, left ideals, right ideals, all are different again. So
thank you very much for this talk. Thank you for the question. I'm sorry, I had technical difficulties. I was disconnected for a while from the session, but
yeah, some I think some questions asked by
other question.
Sí. Other question, Kosham.
Yes.
I would like to also to ask the question, what do you see any possible application of those groups in physics?
N groups in physics. I'm not exactly sure, but there are several applications in dynamical systems and symbolic logic, many, but exactly physics, I'm not sure. Incomplete block designs, of course, in planarity and block designs, etc. There are several applications, but exactly in physics, I am not sure. Probably in planar nearings, there are some applications, of course. Yeah.
Thank you. Other questions, please? If not, we thank the speaker, and now we will have a 40 minutes break before the presentation of Garrett subject. In my time zone, it will be break until 11. In Mexico City time zone, it will be a break until 12, and please calculate whatever. So we have a break. Thank you.
Yes,
Thank
thank you to you. We come back to the 12. Thank you.
Yeah, it's at 1 o'clock here, my time, but isn't it?
Do you have a question, Professor Garrett?
No, I don't. I was just commenting that my time it's 1 o'clock, but that's fine. 12 o'clock your time.
Okay, we have about the 40 minutes break.
Okay, fine.
Okay, thanks. Gregor, is there a question? You can open your microphone.
Creo que no.
I guess that Koshan is having a small problem with the raising hand feature.
Okay. Okay. And, then we go to the break. Thanks.
Entonces, ¿podemos ya lanzar la actividad cultural?
Sí, por favor. Sí.
Ok. Para que van la enlace.
Sí.
Ok.